talk again. What would you like me to say? Does this work? Does it not? Hit the delete. Stand by. Testing 1, 2. Got this, Keith? Okay, you can mute it.
Again, sorry for the delay, folks, and so let's go ahead and start. So good evening. My name is Paul Shand. I am the head of the physics department here at UNI, and welcome to the 2022 Begeman Lecture. The lecture series is made possible by the great generosity of the Jordan family. Richard Jordan and Frances Jordan are grandchildren of Louis Begeman, the first head of the UNI physics department. Begeman, under the supervision of Nobel Prize winner Robert Millikan, carried out the first accurate measurement of the charge of the electron using water droplets. Richard, who has attended this lecture every year, was unable to make it this year. Still, let us applaud Richard for his indelible influence on the UNI physics department. The 2022 Begeman Lecturer is Dr. Carrie Pint. He is currently the Charles Schaefer Chair of Engineering and Associate Professor at Iowa State University. Prior to arriving at ISU in 2020, Dr. Pint was on the faculty of the Department of Mechanical Engineering at Vanderbilt University for 8 years. Before that, he was a research scientist at Intel Labs. Dr. Pint received his BS in physics from UNI in 2005, a PhD in applied physics from Rice University in 2010, and completed postdoctoral training at UC Berkeley. Dr. Pint has over 120 publications and holds 17 US patents. He is the co-founder and CTO of SkyNano LLC, which utilizes economical electrochemistry for the synthesis of carbon nanomaterials from carbon dioxide in air. Dr. Pint is a Kavli Frontiers Fellow of the National Academy of Sciences and was named one of Forbes magazine's top 30 under 30 disruptors in science and innovation. The title of the 2022 Begeman Lecture is Batteries and Beyond: Advances to Address Critical Challenges in Energy and Sustainability. Please join me in welcoming Dr. Pint back to UNI.
Thank you so much. All right, thank you so much, everyone. It's really such a pleasure to be back here at your alma mater. I mean, 18 years since I did my degree here. And I was sitting in the classrooms here. So I'm going to tell you today really about just kind of a couple topics that I'm quite passionate about, places where my team has worked, that I think we made some impact, but in a very broad and hopefully general sense that introduces you to these ideas. And the first thing I was going to do is to ask everyone, you know, what they see as being the biggest challenges in the world today. And, you know, generally I've done this before, and I get a number of answers. I mean, one of them today, if you pull up the news, you probably see war, right? Yeah, that's a big problem. And there's other things that'll come up, like water shortage in Africa, and you know, it's coming to California. Climate change, yeah, that's up there too. We're reading about that. And there's other things like health and food and disease and poverty, right? And these things are there too. And you say, well, but Pint, you're talking about energy. So yeah, energy is there too. Well, you know, one of the things about physics is that when you look at an equation, you want to be able to separate out the independent variables versus the dependent variables. So let's imagine something. Let's imagine that we had unlimited amounts of energy in the world today. And so the question is that if that was the case, which one of these things would change the most, right? So if we had unlimited amounts of energy in the world, we'd be able to clean water, right? We have a lot of water, right? Perhaps we wouldn't fight so much about energy resources, right? You know, all these other things, agriculture, food, and energy are connected, right? We'd be able to grow more efficiently, food. You know, poverty, health, disease. I mean, if you look at third world versus first world countries, what's the difference, right? Energy availability. So why do I work on energy, right? I work on it because it is the thing that if you're able to solve it, then you're able to impact all these other things, except climate change, sustainability, right? So that really depends on where the energy comes from. Because if we burn energy that put CO2 into the atmosphere, or greenhouse gases in the atmosphere, then maybe we make this worse. So let's talk a little bit about emissions. So carbon emissions, where do they come from? Well, if you look at the carbon emissions today in the US based on 2015, 35% comes from electricity, 32% comes from transportation. That means over 65% of our carbon emissions that are coming out today are coming from these sources. So, and these emissions are increasing. I mean, increasing because our global population is increasing because our technology is demanding more power, right? So these trends are getting worse. Well, let's think about the impact of emissions, right? So what does carbon emissions do? Well, actually, just a few days ago, I looked at the observatory in Mauna Loa, Hawaii, and the emissions level, carbon dioxide in the atmosphere, is 421 ppm. That's crazy, because when I started talking about carbon emissions, it was less than 400, right? What does this do? Well, when we start to get into this range of 450 to 500 ppm, we start hitting some red flags in terms of what it's going to do to the air in our environment. It's going to make it toxic. It's going to create things in our environment that we don't quite understand yet. But thankfully, we have some help in understanding that from physicists who recently won this Nobel Prize, right? So in 2021, the Nobel Prize was given away to two physicists who actually described the concept of global warming and how these greenhouse gases affect the climate and heating of the Earth. And this guy over here, I mean, he's not going to have a home too much longer if we keep going at this pace. So this is something that, you know, sort of rings to me. We can argue about this. A lot of people do. My job as an engineer is to try to address and solve this. Well, let's think about energy. So I told you that, you know, the two biggest areas, transportation, electricity. Well, you say, okay, Professor Pint, yeah, I know how to do that. You know, you just put solar cells instead of this dirty energy, right? That solves the problem. Well, it really doesn't. And why doesn't it? Well, because of this concept of reliability. So when you think about renewable energy, right, so you put a bunch of solar cells in place, and then what happens is that you're really dependent upon the variability of the sun shining, right? So when I think of conventional power generation, I think of it as being like well-trained Marines. They're disciplined, right? You can predict every movement. You know what they're going to do next because it's a script. For renewable energy, I think of it like Rambo. So, you know, when I was growing up, you watch movies, Rambo runs through the jungle with a machine gun. You don't know what he's going to do, right? Very unpredictable. And that's what renewable energy is, and that's what makes it difficult to incorporate high amounts of renewable energy onto the grid. And so the challenge is, how do we move forward in the energy picture in order to generate better sustainability? Well, an answer to that can be batteries, right? This is why I work on batteries. This is why I'm interested in batteries. And one of the things you can do is you can combine with these solar cells some batteries. And what it allows you to do is to take the energy that you produce from the sun when it's shining, and you can discharge it later when people need it, right? And in fact, there's been some really nice work. And so this team at NREL has spent many, many years working on this. And this curve that you see here, basically this shows you that as you increase the amount of renewables, so wind and solar, some of things we have here in Iowa, on the grid, at some point you end up with so much variability that you literally have to throw it away after about 15%. That's the word curtailment over here. Throwing it away, getting rid of it. You're producing it, it's not worth anything, right? But if you just take that amount of renewable energy that you're producing and you put 5% of energy storage, batteries, with it, right? Now all of a sudden you shift that curve substantially, right? So it shows you that batteries present an option to propagate renewables on the grid. The other thing I'll talk about batteries, and this comes from my experience at Intel Labs, right? So you can go and you can think about the next biggest invention that you can imagine, right? You know, the next coolest robot, the next coolest drone, prosthetic that moves on its own, right? But ultimately, when you get into the design of things, what you end up with is being limited by the power system, right? So if we want to create new inventions, we want to invent things that change the world in the future to make our lives better in society, batteries are going to be a big part of that as a power system. Now, one of the things I want to emphasize in batteries, a lot of you probably say, okay, I have a cell phone. This has a battery in it. That's pretty cool. Turn on my light. But actually, your cell phone's pretty expensive. And so you don't really think about the amount of cost of the energy that it takes to charge the battery in your cell phone, right? So what the semiconductor industry does, they generate batteries that are pretty expensive, that allow you to have the power requirements so that you can play games or do whatever you're going to do on your phone. But of course, what they don't tell you is that they die after a few years, so you'll buy a new cell phone. Because actually, most consumers, what you find is that after the battery dies, they go find a new cell phone, right? Electronics industry loves you for that. But on the other hand, when we start thinking about putting batteries at the scale of countries, right, which is in our future, things are a little different. And why is it different? Because when you get your power bill from the utility company, it tells you how much you've paid. It may say, look, Carrie Pint, you've paid 12 cents per kilowatt hour, okay? Well, if I take this and I say, okay, $250 per kilowatt hour is what this battery is. I'm using this for 1,000 cycles. Do some simple math. How much am I paying? 25 cents per kilowatt hour. Oh, but wait, the cost of my energy is 12 cents per kilowatt hour. That doesn't make sense. It doesn't make sense to pay more to store the energy than the energy itself, right? Which is why cost is such an important part of batteries when we start thinking about using it on the grid or using it for large-scale electricity systems. Okay, so I'm going to tell you today about really two things. Okay, the first of these is some of the work that we've done on batteries that I think is going to impact your life going forward, right? And hopefully I'll make a case for that, where we've invented a new battery system that has the potential to actually meet the demands for electricity. The other side of this, I'm going to tell you about our ability to convert CO2 from the atmosphere into useful, valuable things in a way that in some states is carbon negative, okay? So let's talk a little bit about batteries. All right, we've all heard the term lithium-ion battery. So when I think about a lithium-ion battery, you see all these little things labeled. I think about a symphony. You go to a symphony, you hear lots of different sections working together in the symphony. But the music is beautiful, right? It's resonant. All those sections work together. That's exactly the way a battery works. So the key notes, the key sections in a battery are going to be your electrode materials that actually store the charge. On the cathode, I'm going to call this the cathode, you have typically some metal oxide that contains lithium, okay? And so it naturally contains lithium, things like lithium cobalt oxide, for example. On the anode side, we have a material that likes to absorb lithium. Imagine it as a sponge for lithium, that when you take the lithium from the cathode, you can literally just go put it into the anode, and it's happy there, right? So a good material for this that we've used is graphite. The other parts of the symphony is this little thing in the middle. We call it a separator, right? This is a Kleenex. It's literally something that is porous. It absorbs the electrolyte that allows the ions to move back and forth, but it also electrically isolates these two electrodes so they don't short each other. The last two parts of the symphony are going to be the current collectors, right? On the anode side, the current collector is copper. We use copper because lithium reacts with aluminum, so we can't use aluminum. But on the cathode side, on the cathode side, we use aluminum because it's cheap and it's light. And so it's a more economical material. So let's go back to 1976. What did we do in 1976? Yeah, batteries have been around for a long time, almost 50 years, surprisingly. But this was actually the first demonstration of a lithium-ion battery. And so this was done by Stan Whittingham, published in Science in 1976. And what he did, instead of using that nice little anode that I showed you, right, so I'm showing you graphite over here, he actually used just pure lithium metal. Okay, he started with lithium metal. And over here, he used a metal sulfide, titanium disulfide, which is a material that likes to absorb that lithium metal. And then he charged it back and forth. And the biggest idea here was that once he took the lithium from this side and put it over here, he could actually take it and put it back, right? Wasn't so good, very inefficient. Turns out lithium reacts with everything. So he didn't get great performance out of it, but ultimately it created the basis or foundation for the energy storage battery community. Let's go 40 years later. What are people trying to do? They're trying to do the thing that Stan Whittingham tried to do early on. They're trying to use lithium metal as an anode. Why are they doing that? Well, over here, I was talking about this graphite anode, right? The graphite's pretty heavy. You store 1 lithium ion per 6 carbon atoms in graphite. So it adds a lot of mass to your battery. And why does that matter? It matters because when I talk about the energy density of a battery, that it's basically how much energy the battery can store versus the total mass of the battery. So if I reduce the mass, all the better. So why not just use lithium, right? Well, the problem is that a lithium is one of the most electronegative materials on the planet, right? Its reduction potential is the greatest, which means, or greatest in a negative way, which means that it reacts with everything when you reduce it. And so today, people still haven't been able to do this. I'm an editor of the top energy storage journal in the world, and I get so many papers on this, and people still are not able to get above a 99% charge efficiency. What does that mean? That sounds pretty good, 99%. Well, if you think about that, what that means is that you move 100 lithium ions, right, and you only get 99 back. One of those lithium ions goes into some side reaction that's not good, and you don't get it back. Well, industry says that your battery's dead at 80%. So let's do the math. You do this, you lose 1% of your charge every time you cycle it. Oh, that's 20 cycles. What good is a battery that only lasts for 20 cycles? This is the state of the art in this field, and everyone's calling this the holy grail of batteries. So what we did is we said, all right, we're not going to follow the crowd, right? Don't follow the crowd into a flame where you know that the physics doesn't work. So we said, let's look at sodium, okay? Sodium's an interesting material because, first of all, it's 1,000 times more earth abundant than lithium. It's not limited by supply chains. Lithium is located in Chile and China, 2 places. Sodium's everywhere, right? The other neat thing about sodium is that you can actually use aluminum instead of copper on the anode side, for a reason I'll emphasize to you earlier. But when we got into this, it was kind of bittersweet because the research community in the battery world, they said, you're silly, you're stupid. Why would you be focusing on sodium? Let's look at the stats here. Sodium, it is heavier, 3 times heavier, right? Right? And it's bigger, right? By quite a bit, 30% or so. And on top of that, the reduction potential is less. What does that mean? It means that if I put 2 electrodes together, I get less voltage out of it. That's not good. So I get less energy. It's going to be heavier. And the result is that, well, I make the same cell, the same sodium-ion cell. It's more expensive, and it's bigger. Why would you do that, right? Everyone said, why would you do that? But we found something else. It turns out that the electrolytes that we use in lithium-ion batteries, it's basically this group here called the alkyl carbonates, right? The reduction potential of lithium is up here. So in order to actually, I guess for a physicist, you would think of these HOMO-LUMO bands as sort of like the equivalent of valence conduction bands, right? These determine the stability of the material. So if you have a reaction that happens out here for the alkyl carbonates, this is going to react in order for this to reduce. It's not going to work. But the beautiful thing about sodium is that its handicap makes it beautiful, right? Its handicap is that it has a lower reduction potential, which means that, it's actually stable within one of these electrolytes, within one of these HOMO-LUMO bands. And what that tells us is that we can actually use sodium as a metal. People are trying to use lithium as a metal. We can use sodium as a metal, and it's stable. Whoa, the physics work, the chemistry work. Let's look into this. So we actually chose, out of this group of ether-based electrolytes, we chose diglide. It's a funny story. Actually, when they first started developing batteries back before 1991, when they were commercialized, they used ether-based electrolytes. Why did they switch to carbonates? They switched to carbonates because of graphite. It's the only reason. Carbonates are dirty, dirty electrolytes, right? Ethers are actually much cleaner. They're much nicer. So we like them in this case. And so The challenge here was to redesign how the battery is developed. Basically, we developed what we call the anode-free battery. What does that mean? It means this graphite anode that I was talking about, lithium-ion batteries, we're just taking it away, right? We still have the electrode there, right? So we have a positive and negative electrode. That'd be weird if we didn't. But we're actually just taking away this material. And so from the cathode, which originally contains some sodium, we are simply just plating metal onto that surface, sodium metal. And so the challenge here is that we don't understand the physics of how that works. So we literally had to start at ground zero in this project to design this system by understanding how to control metal nucleation at surfaces. So what does our batteries look like? Well, when we first started testing these, we do what we call half cells. Half cells are basically batteries where we don't have a cathode. We're just taking sodium metal and then another electrode, and we're just looking at how the sodium moves back and forth, right? I'll show you batteries that we develop later, but these look like those little batteries that you get, if you open up your watch or something like that, you see these little coin things. That's what we make in the lab because they're small and we can test them. And so basically our sodium looks something like this, right? And we put that with a separator and another electrode. We seal it inside this little coin, and then we go ahead and test it. Now, what are we testing? So the most common way that we test batteries is something that we call galvanostatic cycling. All that means is that we apply a constant current to the battery as we're cycling. So we apply a constant current, right? We end up getting this process where sodium nucleates on the other electrode, and then it just continuously grows, right? We stop the current here, and we switch the polarity, right? So we turn the current the other way. We turn it positive if we're making it negative in the beginning. And then it slowly strips off, right? But it never comes back to where it originally was, right? You see that there's a little gap between these two curves. And that gap comes from the second law of thermodynamics. Second law of thermodynamics tells you that you never win. You always lose. And that little gap tells us how much we lose, and specifically how much charge we lose. That gives us an indication of the charge efficiency. A typical lithium-ion battery anode will have a charge efficiency of 99.99%, which means that you lose at most 0.01% charge every cycle. So that's our goal. So we put some batteries together just using simple aluminum. And aluminum is much better than copper for the reasons you can see here. It's cheaper and it's lighter. And we observed a coulombic efficiency, kind of jumpy, but 99.3%. Not quite what we wanted. And this comes from the difficulty that, well, we're actually plating metal onto a surface. The surface really matters. Aluminum didn't seem to be that good. Some of these deposits that we made were very big, and they would literally just sort of crack off. And we saw that. So we had to go in and interface and engineer the interface of these materials so that we could get good adhesion of these layers and get better performance. And I won't go through all the details of that, but we tried a bunch of different types of materials. We're engineers, right? And there are materials like tin. Tin likes to alloy with sodium. So that means that tin and sodium like each other. What that means is that when it comes in, you don't see that big spike here that corresponds to nucleation. It just sort of grows, right? They're friends. They like to hang out with each other. That's 99.6% coulombic efficiency, much better. Then we moved to different types of carbons, and we finally got to this carbon. It's a turbostratic type of carbon, carbon black. And we actually were able to achieve above 99.9% coulombic efficiency for this. That's charge efficiency, which is at a point where, hey, now we can call this a real sort of industry competitive anode material for the system. But there's still a lot of science here that we're trying to evaluate. I mean, we're applying machine learning models right now to really understand all the parameters in the system. But this is a really important and interesting area of understanding how the physics of nucleation on these surfaces, as well as the electrochemistry of batteries, are somehow sort of correlated. There's some harmony there between those two things. We don't completely understand it. No one does. So here's what we see. So this is optical microscope images of sodium plating on carbon. When we first do this at a current of 0.5 milliamps per centimeter squared for 10 minutes, you see these little nuclei. So this is in the optical microscope. These are sodium with a background of carbon. We plate for a little longer. The sodium grows. A little bit longer, grows even more. A little bit longer, we get this really nice uniform film at 8 hours of growth. We can take this to a microscope which uses electrons instead of light. Because electrons have a much smaller wavelength, we can see much smaller features in this material, and something fascinating happens. We have this crystalline sodium film. So I get asked the question all the time, hey, Professor Pint, you know, lithium forms dendrites. Sodium should too. No. Lithium forms dendrites because it's unstable in liquid electrolytes. This is stable. So it plates as a crystalline layer, right? There's no side reactions that would cause instabilities, things to break down, and as a result, dendrites, which would catastrophically short and destroy the device. So this was fun. So we now know that sodium works really well. We made our little half cells. Now we're actually going to move on to making full batteries. So when we went to choose the cathode for the battery, we took some inspiration from a material called fool's gold. So if you ever walk into a rock shop, you know, and you see these box of materials or box of rocks in the corner, and they're, you know, they look like gold, but you can afford them, it's fool's gold. It's iron disulfide, and it's actually a very common material on Earth because it's a byproduct of coal mining. And in fact, we use it in batteries already. So if you go to the store and you get a lithium primary battery, so it looks like a AA battery, but it says lithium on it, it has lithium, or excuse me, it has iron disulfide in it. And the beautiful thing about this is that iron disulfide, when we think about transitioning from a lithium battery to our sodium battery, if we use this as our cathode, the only materials that we have in this are sodium, aluminum, which is our current collector, and iron. That's it. Oh, we have sulfur too, but sulfur's cheap. As opposed to things like cobalt. There's a big problem right now in batteries because the way that we get cobalt from the supply chain is that you have kids in Africa mining it with their bare hands. It's carcinogenic. It's toxic. It's not a good supply chain issue to have, right? How do you scale that up? And so we're moving to a battery system that's earth abundant, it's cheap, and it turns out it works pretty well. So we made some batteries, and the way that we did this is we took this pyrite material, this fool's gold, we sodiated it, which means we stuck sodium into it to make it a cathode that contains sodium to begin with. And then what we did is we simply just charged it and discharged it back and forth. Took the sodium over here, plated it onto this carbon layer, and then plated it back over and over and over again. And that's how we charge and discharge our battery. Now, this is pretty exciting. When we did this, we are actually able to measure, so these are charge-discharge curves from the battery, but more importantly, when we integrate the area underneath that curve, which gives us the total energy stored, and we divide that out by the total mass of all the materials, we get the total energy density of our battery. So relative to the materials of pyrite, sodium, and the nucleation layer, the carbons that we use, which are super thin on the surface, we were able to get energy densities of about 400 watt-hours per kilogram. Well, that's pretty good, right? So, okay, what does that mean? A lithium-ion battery today, state-of-the-art, 150 watt-hours per kilogram package. That means all the packaging, everything contained in it, right? Active materials, you'd think that's about double that. So it's about 300 watt-hours per kilogram. So we are right now, with this battery system, at a level where we are competitive or slightly higher than state-of-the-art lithium-ion batteries, but yet, cost-wise, we've literally reduced 70% of the materials manufacturing cost of this battery. So this is pretty exciting. You say, well, you know, did you move past coin cells? Yeah, I mean, we did. And we worked with a lot of other cathodes, and I could go for a long time and show you all the work that we've done on this. Actually, 2/3 of my group currently works on this project. A lot of great physics in this system that we're looking at. But one of the cool things in this, and this is the great thing about being a researcher, is that we tried to file a patent on this. Vanderbilt said, nah, sodium's not going anywhere. Brought it to Iowa State. Iowa State said, nah, sodium's not doing anything, nah. Just this year, CATL, the world's largest battery manufacturer, said sodium batteries are the future for electric vehicles. You can look it up. They're going to be putting this on their pilot lines. They supply batteries to NIO. They supply batteries now, because of the supply chain issues at Tesla, right? What do? They took the system that we developed, the anode-free sodium battery. This will be in your vehicle in 10 years if you buy an electric vehicle. I guarantee it, which is really, really exciting, right? So they're putting this on their pilot manufacturing lines, and they're claiming packaged 200 watt-hours per kilogram. Now, if you look at the numbers that we got, 400 watt-hours per kilogram, divide that by a factor of 2, that's about what we got. Interesting. Interesting how that works. This is really exciting. And it's a really exciting thing about being a researcher. You know, you can read about Thomas Edison, man who invented so many things as a physicist, but he never really made any money from it because all these corporations took his ideas and sort of ran with it. And, you know, that's great, you know, but at the same time, it's really nice to be able to say that the work you're doing makes impact, and that's the benefit of working in a field where if you make an advance, it can impact billions of people. I'm going to talk about this really quickly because I'm fascinated by this, but in the world that we live in, we always think about batteries as being connected into your system just by plugging it in, separate. What if the system itself could be the battery, right? This is something that I got inspired by at Intel, something I worked on for a while, and yet once again, I'll tell you, I went to a faculty interview. I won't say where. And I told them that I'm going to do this, and they said, sit down, this makes no sense. Makes no sense. We don't want walls that explode. Okay, so we went forward to making structural batteries, right? And so what these are, basically, we did a lot of work on this. We've been working on this and failing at it for many years. But we actually got a project with NASA where we were set up to build a CubeSat, a small satellite, out of structural batteries using materials that are consistent with the reinforced lightweight carbon materials that they use in their aircraft, right? So we actually set up a plan to do this. We simply used carbon fiber, epoxy. We used standard processing techniques, but we integrated inside of the system, you know, lithium iron phosphate, which is cathode material, graphite, which is an anode material, and we put a little bit of ionic liquid, which is a material that allows ions to move back and forth sort of in between this composite. So we were able to develop these carbon fiber composites using standard processing techniques, which are also batteries. They look like batteries. And in fact, you can see it here. I actually have some demos. If you want to come in after the talk, I meant to bring them up here with me. Some plates where they actually, you can hold it. It's a battery. It's a structural composite, right? And so this is what they look like. And when we're looking at energy density, you say, oh, the energy density isn't very high. But actually, this is the energy density relative to everything. The carbon fiber, the epoxy, everything. It is a system that stores energy, no longer a battery that stores energy, right? So we were able to then go forward with the idea of building a small cube satellite. And now a cube satellite, one of the things about a cube satellite goes up into space, and guess what it has in it? It's a lot of batteries, right? And these batteries take up a lot of volume, and it's very expensive to throw things up into space, like huge, huge cost, right? So the challenge was to consolidate those batteries into the structural frame. And we did that. We 3D printed a CubeSat frame. We developed these sides, which are structural batteries, and we were able to use the actual structural core itself. Oh yeah, you can see the video. I mean, we're taking this grindy fan here, and we're simply just powering it. Over here, we're powering an LED. And there's no batteries. It's just the carbon fiber reinforced composites. It's so cool. I really love doing this. Again, if you want to see these, I brought some with me. You can take a look. Now, again, this is fun. Now, Tesla didn't steal our ideas. But a battery day is fun for me because everyone was negative about structural batteries. Battery day 2020, 9/22, Tesla came out and said, what are they doing? They're making structural batteries. What does it do for our Tesla vehicles? Oh, it gives a 14% range increase and a 10% mass reduction. That's pretty exciting. Now everybody thinks structural batteries are great. And then I got a whole bunch of requests for review articles like, you know, Professor Pint, you know, please write about structural batteries. We just saw that Tesla's doing this. It's like, where were you guys 6 years ago? Okay, well, good times. All right, so the next thing I'm going to talk about, I'm going to briefly go over what we've been doing with CO2 capture and conversion. Now, I've talked a little bit about the problem of CO2, but a lot of people talk about the problems of CO2. I don't want to talk about that today anymore. I'm going to talk about solutions, right? We're in the field of making solutions. So if you look out there, how do we fix the CO2 problem? Well, there's some interesting things that have been done. One of them, you can integrate carbon dioxide into concrete. Okay, concrete's cheap. Concrete itself, ironically, is one of the biggest carbon emitters out there. So that's not good. But maybe that makes it a little better. There's been a huge research interest in making methanol from CO2. And still to date, there has not been a single report of a process that achieves more than 1% efficiency in doing this. In addition to that, methanol is pretty cheap. If you add a few extra electrons to this process, then you get ethanol too. You can use ethanol. But again, like, you know, you're using a lot of expense for a very efficient process to get something that is ultimately pretty cheap, and you're going to burn it and create more CO2 anyway. So what's the point? The definition of entropy. The other cool one is basaltic rock. So there's, in Greenland, a power company, which realized that they can pump their CO2 underground into volcanic lava streams, and if they do that for long enough, at high enough pressure, the lava stream will crystallize into rock, basaltic rock, and it will store the CO2. That's pretty cool. And my kids love rocks, but I have to ask the question, what's the value, what's the cost, and what's the need? Right? This is the way our world works. It works based on economical considerations. It doesn't work based on cool science, unfortunately, most of the time. So the other thing I want to highlight, and this has been in the news recently, is this Shell carbon capture plant. And so you can see the picture of the Shell carbon capture plant. It's been in operation since 2015. It's in Alberta, Canada. You know, they're doing some neat stuff. They're taking carbon dioxide. They're going through a process where, you know, they can chemically, you know, store it by compressing it into liquefied carbon dioxide, and they put it underground. And their claim is, well, they've actually, over the last, how many years, 7 years, averted 5 million tons of CO2. Cool. Well, this is what they show the public. The public doesn't understand this. So what does the public understand? They understand this. Actually, this is what you see if you actually Google Shell carbon capture, right? I don't know if Shell did this, but someone did it. And as a physicist, I look at this and I say, what's wrong? Anybody see something wrong with this in the crowd? Like, seriously wrong. Well, you know, that vacuum cleaner has no plug. Right? It has no plug. What is that? Oh, in thermodynamics, we call that a perpetual motion machine. It is running without any energy input. Right? It's like, Professor Pint, that doesn't matter. Like, it's just for the general public. No, it really matters. It really, really matters. I'll tell you. This is a very important problem in this area. And ultimately, what you see is that actually what caused the controversy that brought this into the news is the idea that an independent consulting firm went and they looked at the carbon emissions from this carbon capture plant and showed that they've actually emitted 7.5 million tons of CO2 since 2015. Okay, so if the whole goal is to store CO2, but you actually have emitted more than you've averted, what are you doing, right? But the public doesn't understand because they don't understand thermodynamics. You never trust someone who's trying to save the world and doesn't understand thermodynamics. Right? It's the story of the day. All right, let's talk about carbon nanotubes. So we have carbon dioxide. We want to make it into something valuable. We chose carbon nanotubes. Why do we like nanotubes? Because it is a super material. Mechanically, it has tensile strength that is 10 times the strength of steel at 1/6 the weight. Young's modulus greater than 1 terapascal. For example, aluminum, Young's modulus is, 60 kilopascal. Electrical properties, it can be 50 times higher than copper, right, in certain types of nanotubes. And thermal properties, it's comparable with diamond. So it's really an amazing material. And so you ask, well, why do we not have the material in everything, right? So we'll get to that. But the synthesis of nanotubes, I'm not going to go through this too much, but just keep in mind, when we synthesize nanotubes, the way it works is it's basically, if you look at a binary phase diagram between carbon and metals, you'll always see this place where you get, you know, metal plus graphite, right? So most metals will actually precipitate graphite out of their metal structure. And so the way we do that is we take a gas like acetylene, you know, acetylene blowtorch, we'll throw it on a metal, and if the metal is really small and it's a tiny little nanoparticle, it'll actually spit out carbon that is small like itself, but in a tube. And we call that a carbon nanotube. And so we need a metal catalyst to do this. That's something that I'll emphasize as we move forward. But carbon nanotubes, well, why aren't they in everything? Well, did my PhD work in a lab that developed the buckyball and worked on carbon nanotubes. And I was always sort of saying, carbon nanotubes, 2 years, it's going to change the world. And that was 20 years ago. We kept saying that. It's just 2 years away. 2 years away, you're going to have nanotubes in everything. Promise. Why isn't that happening? Well, it happens because some realistic issues. First of all is that there's substantial risk in developing systems that tend to work pretty reliably at small scale, but then they're very expensive, large capital expense when you actually make the system. So if I go spend $10 million on this big reactor, I go and I turn the electric switch on, so it's plugged in, right? And it doesn't work. I'm out $10 million. It's not a good day, right? That's happened. Happened many times. That's a problem. Another problem here is that actually one of my great colleagues, Desiree Plata and friends, she stood up at a conference recently very boldly and said, two carbon nanotube people, look, if you all scale carbon nanotube synthesis up to carbon fiber level productions, we will double our global yearly emissions. And she supported that with some calculations in this work. Right? And the reason is because when we throw something like acetylene through some high temperature reactor, a very small amount of that acetylene actually reacts to make the nanotube. The rest, what does it do? It oxidizes, it forms a more stable form, right? What are those things? It's carbon dioxide, methane, not good. Polyaromatic hydrocarbons, cancer, okay? Not good. We're throwing this out into the atmosphere. So this is also a problem. So we have to think outside the box. So what did we do in my team? Well, we developed a system, and this is actually the version 1.0 of it, where we can actually take a carbonate salt, the type of carbonates that they actually use to store thermal energy in the desert. So lithium carbonate, could be sodium carbonate, right? And so we can heat it up, and we'll melt it. Then we use electrochemistry. So we have a cathode where the carbon is deposited, and we also have an anode where oxygen evolves. And I'll explain the chemistry here in just a minute. But the way this works is we stick our electrodes in, we apply a voltage, lab air goes in to supply the carbonate with carbon dioxide, and we break the carbon from the carbonate and actually grow carbon materials and carbon nanotubes, and then this is what we get after we go through this electrochemical process, right? So this is from carbon dioxide that comes directly from the air. Well, how does this work? Chemically, well, we start with something like lithium carbonate, right? On this carbon-collecting anode, we literally just rip the carbon off of that, right? Then this lithium carbonate turns into an ion. It moves to this side, right? And the oxygen over here, O2, evolves off, right? And then we're left with LiO, or Li2O, right? Li2O plus CO2, which comes in from the air, forms, again, lithium carbonate. So it's a completely reversible process. We can reuse the carbonate over and over and over again. And the key thing here is to make sure we look at our reduction potential. This is a key theme, making sure the chemistry and physics works, right? For something like lithium carbonate, the reduction potential of the carbon is going to happen first before the alkali metal, right? So this ensures that we're actually reducing the carbon. We're not actually reducing the lithium or what other alkali metal system that we have in there. Okay, so we're not the first to do this. Actually, carbon deposition on a silver wire was done back in 1966. Just like batteries, it's not a new field, but people haven't actually been able to synthesize valuable materials. They've made a lot of carbon junk over the years. And so when we started this, the most promising one was this work where they made these fibers, which are actually micron sized. They call them nano. But of course, you'll notice that nano, you have to have one dimension less than 100 nanometers in principle to be nano, but they weren't nano. And so they made these materials, and so we said, okay, that's pretty cool. Let's actually contact them. So we got in touch with Stuart Licht, and we did a little clever project together, because he knew the system better than us. That's what we do in science, right? You find someone who knows more than you work with them, right? We literally turned knobs. We played with parameters. Engineers, we're engineers, right? And so we came up with these tubes. We're going to call them tubes, but they had holes in them, right? They're really bad looking nanotubes. They're not really good nanotubes. They're really big, 100 nanometers, 150 nanometers. You know, not what we wanted, but it was really the first demonstration that we can get things with holes in it. Going forward, we said, okay, how do we understand the system and control it to make the material we want? So we went in and we said, okay, let's do some tests. Let's look at these things. If we make these little fiber things, if we use this setup, we're nickel anode, you know, some steel-based cathode, right? And what we found is that always, so this is looking in the electron microscope again, and we're using a process called electron dispersive X-ray scattering that allows us to see the chemical identity of the materials. And so you see this looks like nickel, but we're growing the carbon. The carbon is being deposited on this iron-based cathode. Where's the nickel coming from? It's crazy. Well, okay, this is electrochemistry. So what can happen is that your nickel can corrode into your electrolyte and literally go to the other side. So it like poisons our whole system, right? That's not good. And so we can't grow something good with nickel. Iron is going to always be our best catalyst material. So what we did is we used a process called atomic layer deposition. Basically put a thin layer of aluminum oxide on the surface. Aluminum oxide, it is a stable material. And if you make it thin enough, it prevents this corrosion effect, but it still allows charge transfer back and forth in the system. And also, because that's the electrode where oxygen evolution takes place, facilitates oxygen to evolve. It was like turning on a light switch, right? We saw these beautiful nanotubes, right? 30 nanometers-ish. We saw iron catalyst sitting at the end. Good sign, right? And we were able to successfully produce carbon nanotubes from carbon dioxide for the first time. They were good quality nanotubes, right? And this is an image of it. So this is a transmission electron microscope image. You can actually see the carbon, you know, tube, right? So these are the carbon atoms. Like you're looking at it side on. You can see, if you look closely, the atomic spacing between the carbon atoms in that carbon nanotube matches closely to that of graphite, right? And so this was a really exciting step forward. And we've done a lot of work since then. We've played around with making smaller particles, you know, and really controlling it. We can control the nanotube diameters. Why does this matter? Because, you know, if you go into industry and you want to buy nanotubes, you're going to get nanotubes of about 50 nanometer diameter as sort of the industry standard. That's going to cost you about $200 per kilo. Now, the cool thing with what we're doing here, in a lab scale system, we calculate our energy costs, and it costs us about $50 per kilo to make these nanotubes. Oh, wow, we're doing better than industry. Scaled to ton scale quantities in our little tiny reactor where we haven't controlled anything yet. That's a good sign, right? That's a place where you decide, oh, we're going to start a company. And we did. I'll tell you about that. A key part of this, of course, was the catalyst. You know, and you can actually see, this is, again, imaging where we're able to see catalyst formation, which is enabling our nanotube growth. Now, I've been talking about carbon negativity. Let's break down the numbers. Let's think about the hype. So we've done calculations on this. We can produce 40 grams of carbon nanotubes per kilowatt hour of electricity consumed. Fact. This yields a net CO2 removal of 144 grams CO2 per kilowatt hour. Every company out there which is removing carbon from the atmosphere stops here, right? They stop here. They say, oh, look, we're carbon negative. Oh, but wait. That means that you're connected to some geothermal reservoir, right? How do you scale that up to the size of a global economy, right? It's not really possible. In reality, you have to plug into the electrical grid in the country, right, or in a state. And so what we have to do is we have to sit down and say, are we really carbon negative when we actually plug into the electrical grid? And so in Iowa, where we're at, you can look at Energy Information Agency data, which publishes every year the net carbon emissions as well as the net production of energy. And you can figure out from that with some simple calculations the total gram of CO2 that's emitted per kilowatt hour of energy that's produced. So in Iowa, we're at 354.4 grams CO2 per kilowatt hour, right? South Dakota, which is our near neighbor, 166.95. Washington at 103.34. And the difference between these comes from how many renewables and the emissions of those that are actually on the grid. Now, the cool thing with this is you'd say, well, look, you're not carbon negative in Iowa. Yeah, we produce net positive 200 grams CO2 per kilowatt hour in Iowa. Yeah, I mean, that's true. This is the big picture. This is the reality, right? We're still better than carbon nanotube synthesis using other techniques, but we're still carbon positive. Oh, but wait. We go to Washington, carbon negative. We actually absorb net 40 grams CO2 per kilowatt hour for the nanotubes we make. This is the first carbon negative demonstrated technology that is out there based on being able to plug into the electric grid in any of the 50 states. And we are carbon negative in about 8 states right now. And we're working that down, hopefully, soon. So this has led us to start a company, Sky Nano. We founded in 2017. This is our team, right? So there's me. This was my graduate student. She is now my boss. And so we've been able to recruit some amazing people. Notably, we actually recruited the world-leading researcher in battery manufacturing, who is heading most of the work here in the US in battery manufacturing from Oak Ridge National Lab. He actually left his position to work with our company. So when you hire people like that, you're doing something right, hopefully. And we're working on, right now, kilogram scale applications or production of nanotubes. We're using these in a variety of technology sectors, batteries, tires. We make sunglasses. We've worked with Visa and MasterCard to make credit cards. I mean, we're doing a lot of really fun stuff. One of the fun projects that we've done recently is we've partnered with TVA, which is the Tennessee Valley Authority, and they have this John Sevier 871 megawatt combined cycle plant, and we have set up shop on their flue gas reactor output. And so we're taking CO2 directly from their flue gas output, and we're converting it into nanotubes. In fact, it has worked so well, we've gotten a lot of press. You can look this up. But the CEO of TVA is actually rejigging their plant so that they can integrate carbon nanotube production from their exhaust, which is pretty fun. The other area that we're working in is batteries. So we're actually working in, and I'll skip this slide, working in making extreme fast charging batteries. Batteries that charge, so 6C means that it charges in 10 minutes, discharges in 60 minutes. This is big for electric vehicles. You don't want to be sitting there charging it for 60 minutes. You want to charge it for 10 minutes, 5 minutes, right? And so we're actually able to hit the DOE target with these nanotubes that we're making. We put them into batteries. And as you can see here, we're making pouch cell, which is large cell, like industry-level pouch cells. You get this in a Nissan Leaf, right? This is the scale of a battery you'd get. And we can actually get batteries that last for 500, 600 cycles within the specified tolerance for failure under these charging conditions. So that's pretty exciting. Okay, so thank you for your attention. I'm going to leave it here. I'm done with my talk, but I just want to leave you with a couple ideas. One, for especially students, pursue research that makes impact. I mean, one of the great things about doing research that's impactful is that if you fail at it, right, you can still make impact by helping others succeed. If you succeed at it, you can impact the lives of billions of people, right, which is pretty exciting. And this is what defines my path toward energy. The physics and chemistry don't make sense. Don't be swayed by the opinions of others. A lot of people in academia everywhere have opinions. They haven't done the physics, and you have. Trust your gut, right? Be critical of those who claim to save the world but don't know thermodynamics. Thermodynamics is important. You should take it if you haven't. And great mentors, in this case, save the world through the eyes of the thousands of people that they interact with. And I can tell you that I would not be here if I did not have great mentors at University of Northern Iowa when I was here. In fact, I almost left being an undergraduate physics major to go back in the military. And after a conversation I had with my academic advisor, Professor Paul Shan, I canceled. I ghosted my recruiter on that. And if I wouldn't have done that, I would have been in the military right now, right? I would have never achieved what I accomplished. And for me, it was important. I was a first-generation undergrad student out of my family, so it was a big deal. So thanks to the support that I've gotten from funding agencies, both from Sky Nano, which is this site over here, and my research lab, which is over here, and my students. And of course, I can't emphasize enough that I'm sitting up here talking about this research and things that we've done, but 90% of it's them. Right? They come up with the cool ideas, and I just mentor them to make it successful. So thank you so much. Happy to take any questions. Appreciate you coming tonight.
That was an excellent talk, don't you think? See what happens when you listen to me? Good things happen. All right, so Professor Pint will take questions from the audience. We have 2 microphones in the aisles, and so if you have a question, please use the microphones to ask your questions. So, question time. All right, we have a gentleman coming forward.
Early on in the battery portion of the talk, you mentioned that sodium is a lot heavier than lithium, but then later on you had 400, what was it, energy per kilogram?
Yeah, yeah.
So does that mean your new batteries were like of the same weight, still storing more energy, or?
Yeah, so that's a good question. So because we're using sodium as a metal, so in this case we have no kind of sponge material that we're putting the sodium into. We're getting rid of all the mass of that extra stuff there, right? And it's stable in terms of the chemistry so that it works just as well as the lithium battery, which has that extra material. Now, this is why this is a holy grail for the battery community to do this with lithium, because it's smaller, you know, it's more compact, it's lighter. If you're able to do the same thing with lithium, you would get something like 700 watt-hours per kilogram instead of 400. And so that's what's driving the community. And so everyone's following the big numbers, but they forget the science, right? And so far, no one has shown that the science can work. So yeah, so we're less good than lithium, but we're still better than lithium ion.
Other questions?
Yeah, thank you for a great talk. So I think at one of the slides you showed 10,000 cycles, like sort of a goal. So I was sort of wondering if, in your opinion, that is at least with the current technology, that is the upper limit.
Yeah, it's a great question. One of the neat things about what Tesla's doing right now, if you buy an electric vehicle, you'll notice that your battery comes with something like an 8-year or 10-year guarantee. You know, and so that's already at the ballpark of about 8,000 cycles. One of the challenges we have in the research lab is we don't have the R&D facilities that you'd have at something like, you know, a Tesla research facility to do this. Now we have gotten, and I didn't show a lot of the work we've done, but we can get up to about 400 or 500 cycles with our sodium battery until it hits 80% by playing some tricks on the cathode. And it's pretty stable over that region. Of course, then it hits 80% and goes down. But we could definitely, with sort of the resources of a bigger sort of manufacturing environment, sure, this is what CATL is doing, right? I mean, they're doing this, you know, pushing it up to 2,000, 5,000 cycles by really engineering it intricately to get there.
Other questions? I have one.
All right.
I think lithium-ion batteries have a bad habit of exploding.
Yes.
So does your sodium batteries have the same kind of problem or not?
Yeah, and the problem of exploding is a tricky one because generally, you know, and this happened to Samsung, you know, they'll sell 1 million batteries, and even if one explodes, you know, it becomes a news event, and everyone thinks the batteries are going to explode. But in reality, it's hard to predict against a very rare event. Mm-hmm. And so, you know, our batteries will face that challenge too, no doubt. But what I will say is that a big arm of our research lab right now is treating this not as a materials issue, but as a machine learning issue. So, you know, one of the neat things that we found from our work is that we can predict these types of failure events before they happen by measuring things inside the battery under its normal operation. And then machine learning can predict it, and we can shut the battery off before it happens, right? Before it reaches catastrophic failure. And to me, I think that, you know, a lot of researchers have treated this as, you know, how do we predict, you know, how do we solve a materials problem for something that happens, you know, 1 out of 1 million times, And it's really hard to do that in the research lab because in reality, in a research lab, you're looking at averages over 10,
Yeah.
And so I think that's really where the power of these sort of computational methods applied to systems. I mean, right now your battery is a black box, right? You can't know anything inside of your battery. It just sort of like works until it explodes, if it does, or until it dies, right? And so the challenge is to use the data that comes out of it when you're using it normally to be able to predict those events, and we're doing that.
So perhaps you can answer this as well. Why do they explode?
So the reason why it explodes is because, I was talking about these things called dendrites.
Mm-hmm.
And so when you have an event where, for example, I mean, there's a number of reasons why this can happen, but maybe there's a little bit more lithium that deposits in one area of the electrode versus the other. And so all of those sort of slots in that sponge get filled up, and then the lithium ends up sort of plating on top of that electrode. What happens is that it then reacts with the electrode because it is unstable, right? And then that little piece there now becomes a site for nucleation of growing more lithium. And when lithium grows, it doesn't grow as this really nice, friendly, like planar film. It grows as this tree-like thing that snakes across the battery. When it does that, it snakes across the battery, it will reach the other side. It'll break through the separator, it'll reach the other side. When that happens, it shorts electrically the device. So you have now the system discharges super fast, right, through that electrical short. That causes it to heat up, Joule heating. And your electrolyte, when it heats up, poof, hits its flash point. So that's when it explodes. So it's a complicated system. But it's always that just little defect that happens that causes total catastrophic failure.
And you also said your sodium grows in crystalline form, right?
That's
so
right.
That would tend not to happen.
Yeah, I mean, again, when a dendrite forms, it can be due to some defect in your system that happens 1 out of 1,000,000 cells, right? So even though 999,999 of your cells have crystalline sodium, one of them, which has a little defect in some little concentration gradient or something, it forms a dendrite, it can do the same exact thing.
Yeah,
Right.
That's the one that ends up in my phone.
That's right. You'll get lucky on that one, yes.
All right, any other questions? Okay, Dr. Morgan.
You gave the example of the Cube satellite and then Tesla, right? The thing is the battery.
Yeah.
Pie in the sky, what would you make battery if you could? Like, is there any world in which your house is a battery or this building is a battery, or do they have too long of a lifetime to want to put that functionality into the structure?
That's a wonderful question. So my long answer to this. When I look at history, I always use history as a precedent to predict the future, because you can't predict the future without considering history and the exponential growth that happens in history that you can't predict. But look at where we were 30 years ago with batteries, right? With energy systems. I mean, go to an airport 30 years ago. There's no need for an electrical plug. Today, everyone's fighting over an electrical plug. We all have mobile technologies that require on-demand charging, discharging, and so on. So think 20 years ahead, right? We can't predict what it's going to be like, but I can think about a world where 20 years ahead, we're going to need more on-demand energy, right? How do we get more on-demand energy? Well, I mean, systems have to have energy built in, right? I mean, maybe I charge my laptop by sitting it onto this podium, which is actually dueling as a battery. And so I don't know if that's going to happen. Maybe we'll use lasers to charge things, right? They're already doing that, with military applications. They're taking these drones and they're shooting lasers at them to charge them as they move through the sky so that they can literally run forever, right? Beating the laws of thermodynamics. So, however we do this, I think that there will be a world in the future where energy is so on-demand available that we can access it from anywhere at any time, right? And then at that point, there's going to be this unique intersection between the information of accessing that energy and the energy itself, which is going to be fascinating, right? So we already have a lot of data from our social media, but imagine like this is going to be constantly tracking people all the time based on your energy usage, which is, I don't know, that's the world I see, just based on a historical precedent. Let's see if it comes true. 20 years from now, you can give me a call and say, yeah, no, you're wrong.
to be.
Since at the beginning of your talk you mentioned the effect on geopolitical also, I mean, so in the 20th century it was like fossil fuel which made all of these conflicts in the world. So how are you envisioning like a world with batteries and the geopolitical effects that it may have?
Well, I think that, you're seeing it right now, actually. You look into the news and you look at the supply chain issues that are happening right now. I mean, there's a reason why Elon Musk is so desperately trying to get cobalt out of his batteries. And there's a reason why CATL is moving towards sodium batteries. And it's because from a standpoint of geopolitics, things like lithium, materials like lithium are concentrated in China and Chile. Carbonate materials that actually power batteries in terms of electrolytes are mostly manufactured in China. So what you end up with is a situation where if you have supply chain issues where certain countries sort of control the power over the materials, right, then ultimately if you're dependent upon that technology alone, you run into issues, which is why I really think that sodium is the way to go. I mean, if you're able to take away those barriers and use all materials that are sort of equally accessible anywhere in the world to make batteries, I think that's exciting. I also think that, we did a little project once. It was making a junkyard battery. And if you look me up, feel free to take a look. It's great. We had some pictures in the junkyard holding like chemicals. We went to the junkyard. We found junk metals, like steels and stuff like that. And we went back to battery science and said, hey, look, we can process those junk metals into electrodes using household chemicals. And so we took then those materials, and this is like inspired by Breaking Bad or something like that, right? When they're out in the desert and they like power up their vehicle out in the desert with like, some fruit batteries or something like that. But practically there may be a day where you can literally go just scrap around for junk in your house, put it outside the back of your house, and then literally go off grid and develop your own energy storage platform. And I think that's probably a far reach from the realities of today, but it would be something that would completely decentralize the notion of energy storage and, in some sense sort of build into this maker culture that you're seeing that's coming on in manufacturing with 3D printing and so on. So yeah, crazy stuff for you.
How fast do you think we get off fossil fuels? Just putting on your futuristic hat.
It's hard because at some point you depend upon regulatory details of countries, and I think that what I've seen signaled out of China is they're putting timeframes on the banning combustion engines, right? So if you have major countries which sort of command large portions of the population that says you cannot have a combustion engine, it's against the law, then that's a huge step. And I think that you're going to have to see that type of motion happen in countries to be able to force people away from it. But I think it'll stick around for a while. We'll still fight around with it for a while, but again, the time scale depends upon the regulatory environment and really the sort of, I guess, geopolitics would be the word, between countries and their usage of energy and sort of the acceptance of the role of these resources and the sustainability problem that we'll face. Probably as we face more and more of these problems, you'll see more and more pressure on governments to make those types of decisions. So, that's my take.
Any other questions? One more from the back.
So back to the structural batteries, how does the energy storage over cycles, is that a problem with stuff like your satellites up in space? Do you just leave them up there to die, or? Yeah, so it's a great question, and I often, and this is oftentimes what people say, hey, it's never going to happen. It's like, okay, if you build a house out of a battery material, that's a structural material, and well, the lifetime is 10 years. What do? Rebuild your house, right? And so lifetime is certainly a big issue in this type of system.
I think for things like CubeSats, you'd look at the lifespan of its operation. So that may only be for a mission, for example. And for that, you may need to charge it 100 times. And what we're doing is sufficient for that purpose for NASA. But if you're thinking about, if you're thinking about electric vehicle, maybe you keep it for 10 or 15 years. So it'd have to be functional there. If you're talking about a house, now, it's got to be 100 years. And we're a little ways away from that. So, but it's fun because you can propagate into different technology sectors as you improve the cycle life of the technology, which is fun. Yeah.
Thank you.
Okay.
Any other questions? All right. If not, let's thank Dr. Pint again.
Yeah, thank you.
All right, then thank you and have a good evening. I think Dr. Pint mentioned that he had some demos up here.
Oh yeah, if you want to
So
take a
if you
look at
wanna-
the structural batteries, I have them in my bag. So